Associate Professor and Head of the Department of Mathematics, SDM Institute of Technology, Ujjire. As I agreed, I am going to brief you the content of 18MAT21, Module 3, 4 and 5 in 2 hours. Bear with me if I go fast, as I have to complete within 2 hours. So if you have any doubts, you can ask in chat window at the end of the session. And convey me whether if you feel me going bit fast or slow. According to that, I adjust my lecturing. Okay. In the beginning, I take module 5, that is on numerical methods, because it is one of the modules which is scoring if you are a bit practiced with the calculator usage. So in numerical methods, we are going to study about how to interpolate the things or extrapolate the things. And next, how to solve algebraic and transcendental equations using two methods, which are Newton's-Raphson as well as regular Farsi method. And lastly, how to do numerical integration using three formula that is constraint your syllabus. There are many formula, but your syllabus is constrained to those three. Okay. First of all, we should know what is numerical methods. It is new method of area of study. Actually, numerical methods are the recent development due to the computers. So till now, you have studied from your childhood to second PU about analytical methods. For example, if you want to solve algebraic equations of second order, say quadratic equation, then you know how to get the root of it, as using the formula x equal to ax square plus bx plus c equal to 0 is quadratic equation. And if you want the roots of it, you are preferring the formula x equal to minus b plus or minus square root of b square minus 4ac by 2a, or using calc, or by factorizing the quadratic equation as product of two linear factors, you are getting the exact roots of it. But in numerical methods, it has certain drawbacks also. As we are not getting all the roots, we are getting one of the roots, and particularly real roots. And methods, we are not going to get exact root. We are approaching the exact root by repeating the iteration formula. So in numerical methods, usually you have iterator formula or recurrent formula. The name itself suggests you are repeating the formula many times. So as many times you do, then you are approaching the exact root. You are closer to the exact root. So in computer, if you write a program with looping, then it can do infinitely many times the repetition of the formula within a fraction of second. And if you are written the program properly, then whatever the difficult equation it will solve and give the approximate solution for it. So due to computers, this field is developed. So this is the introduction of numerical methods. Now, I first take the first part of the syllabus. It is about interpolation. Before moving on to interpolation, we should know certain basics of applying certain terms to interpolation formulae. They are nothing but finite differences. What is finite difference? Again, in finite differences, you are defining those finite differences for equal intervals as well as unequal intervals. First, we see finite differences for equal intervals. Okay. So, while interpolating or extrapolating, again, you we'll come to know what is the interpolation and extrapolation later. So it is our motto in this section. So interpolating and extrapolating the unknown function. We are preferring two types of finite differences for equal intervals. Say the unknown function is y equal to f of x. It is not known to you, but they'll give n plus 1 set of values of y0, y1, y2, etc. yn corresponding to equidistant values of x. Say x0, x1 is x0 plus h, x2 in terms of x0 is got by adding 2h to x0. Similarly, the nth term xn is got by adding n times the step length term h to x0, where h is called as step length or step size of the interval, which is the difference between two consecutive values of x, and it should be equal because we are preferring here equal intervals. So for those values of x wherein the difference between two consecutive values of x are same as h, then we are having those values of x together with their corresponding values of y of the unknown function y equal to f of x, where y is depending on the independent variable x there. Then first we understand what is finite forward differences for equal intervals, and later the finite backward differences for equal intervals. First we prefer finite forward differences for equal intervals. So as I said earlier, we are preferring the observed values, n set of values, y0, y1, y2, etc., yn, they need not be at equidistance. They are only depending on y equal to f of x relation. We are getting the values for that. And they are the set of values of an unknown function y equal to f of x corresponding to n plus 1 equidistant values of x. The initial value of x we given we are taking as x0, and x1 is got by adding h to initial value, and we mention it as x1. Then x2 as x0 plus 2h. Actually x2 got by adding h again to x1, but here we are preferring to represent every values of x in terms of initial value. So therefore x2 we will get by adding 2h times x0. So nth term obviously will be x0 plus nh, where h is called as step length or step size of the interval, which is the common difference between the two consecutive values of x. Then we are going defining first order, second order forward differences as in general nth order. So first we focus on first order forward differences along with backward also. Together I will take to save time. So first we focus on first order forward differences. So it is represented by the notation delta. Backward is by nabla, pronounced as delta for forward difference, nabla for backward difference, and is defined as first order is defined as delta is an operator. First order it is because power of delta is or degree of delta is 1 here, and it is operating on always y. Y is function of x. So delta is operating always on y or f of x. Y is equal to f of x. So what we do as forward term says, we have to go for the forward value of f of forward value of x. So if you add h to x, you get next value as x plus h. So its functional value you have to take first. First go forward, get the functional value of the next value of x by adding the step length, then subtract. So again the name indicates forward difference. So you have to take the difference with the value you need, f of x. So from the term itself, you understand what is first order forward difference. It is the difference between the next value of y, or it will be f of x plus h minus that y or f of x itself. So this is how in general we are defining the first order forward difference. So we will apply this general definition to particular values now, because you are having n plus 1 set of values of y corresponding to n plus 1 equidistant values of x. So what is it? Some of the first order forward differences are, first is we are operating delta on first value of y, it is y0. So what is delta of y0? Delta of y0 is you go forward of y0, where you reach you reach at y1. So f of x plus h becomes the functional value of y or functional value of x to the next of y0. It is y1. So y1 minus the value itself. It is y0. So this is how we are defining the forward differences. Next, similarly, what is delta y1? It is go forward of y1, you reach y2, then take the difference with the value you are operating on. It is y1. So you can go up to delta yn minus 1 only, not up to delta yn, because delta yn minus will be go forward of yn minus 1. Previous value is yn minus 1. Go forward of it, you reach yn minus the function itself. So note that since delta yn is what? It is go to forward of yn plus 1. Is it defined here? It is not given in the set. In the observed value given, it is not there. So therefore, you can't able to define delta yn in the given range. So therefore, note that since delta yn is yn plus 1 minus yn and yn plus 1 is not known to us, so we can't define first order forward difference for delta yn. You can go only up to delta of yn minus 1. That is one lesser value of the set. So forward differences goes on decreasing the last value. You will understand it later. Okay. Similarly, as delta yn does not exist, because delta yn is yn plus 1 minus yn plus 1 is not known to us, therefore it is not existing, therefore you can define only up to delta yn minus 1. Which one? First order. So similarly, at the same time, I'll take here itself the backward difference. So what is delta of nabla of f of x? Nabla of f of x is start with the value. You are not going back. You start with the value, then take the difference and take the functional value of the backward value. If you go backward of x, it is you have to subtract h from x. So f of x minus f of x minus h. So name itself suggests that backward difference is functional value of x minus backward value of functional value of backward value. So this is how we are defining the first order backward difference, and this operator we call it as nabla. So we see certain first order backward differences for the given set. What is nabla of? Again you see nabla y0 you can't define. Why? Because you are starting with the y0 minus previous value, it will be y suffix minus 1. Is it there in the set? No. So therefore, in backward difference, as we seen in the forward difference, last delta yn is not existing. Here nabla y0 is not existing. It will start with nabla y1. What is nabla y1? It is start with the value minus the previous functional value. It is y0. See there, this is also y1 minus y0. This is also y1 minus y0. But this is first order forward difference of y0. But this is nabla or first order backward difference of not y0. It is y1. So getting the value with the same manner, but representing for different values of y. This difference you should know. Okay. So delta y0 is y1 minus y0. The same as nabla not y0. It is y1. So are you following? I hope you are following that. Then nabla y2. What is nabla y2? Start with y2. Take the difference with previous value. It is y1. So previous value of y2 is y1. So y2 minus y1. Similarly here you can go up to nabla yn. For backward differences, all the last values exist. First values are goes on decreasing. So nabla yn is yn minus 1. This is also there. So here also you note that since nabla y0 is y0 minus y suffix minus 1 and y suffix minus 1 is not known to us, therefore we can define first order backward difference starting from nabla y1 itself. So I hope you understood that difference. So we move on to the next slide now. Similarly, we can define the second order forward differences, and notation for it is delta square, or for backward it is nabla square, and pronounced as delta square and nabla square, and is defined as what is nabla square of f of x. It is nabla of f of x plus h. Before you had nabla of f of x as f of x plus h minus f of x. Now for each term you are applying nabla. So nabla of f, sorry, not nabla, here delta. So what is delta of f of x? It becomes delta square of f of x, and f of x plus h, on that you are operating delta. So delta of f of x plus h minus delta of f of x. So some of the second order forward differences are delta square y naught. What is delta square y naught? Delta y naught is y1 minus y naught. You apply delta again on both sides, you get delta of y naught is delta square y naught, and y1, for y1 you are applying delta, so delta y1 minus delta y naught. Similarly, delta square y1 will be delta y1 is y2 minus y1, so delta square y1 will be delta y2 minus delta y1. So you can define like that, and you can only go only up to delta square. Delta you can go up to yn minus 1, but here delta square you can go up to only delta square yn minus 2. You can't define delta square yn minus 1 as well as delta yn. Similarly, nabla square f of x, it is given by nabla f of x minus nabla f of x minus x. Now we see some second order backward differences. Nabla square y2. So again, nabla square y naught is not defined. Nabla square y1 is also not defined. It will starts with nabla square y2. What is nabla square y2? Nabla y2 is y2 minus y1. Apply nabla on each term. You get nabla of nabla y2 becomes nabla square y2 equal to nabla y2 minus nabla y1. So like that you can go on defining it. Last value here exists. Only first two values are missing. Again, I have mentioned why it is so. I hope you understand. I don't want to repeat the narration there. So I move on to the next slide. Don't worry much on where all existing. Just understand how we are defining. That is for exam sake, that is more than enough. Now we move on to third order. Similarly, we can define third order, fourth order, fifth order, up to nth order, forward as well as backward differences, and they are denoted by delta cube, delta to the power 4, delta to the power 5, etc. delta to the power n respectively. And these backward as well as forward differences can be systematically put in a table called diagonal finite forward difference table or diagonal finite backward difference table. So in one table itself, you can show it because way of doing is same, but only representing that particular value is differing. So therefore, in only one table, I can define both forward as well as backward differences. So first column is for values of x, x0, x1, etc. up to xn. Here I took for simplicity only 5 set of values of x as well as y. So next column for y, corresponding values of y for f of x naught is y naught, f of x1 is y1, f of x2 is y2, f of x3 is y3, f of x4 is y4, and f of x5 is y5. Now I define delta. So what is delta? As well as in the bracket nabla. So what is delta? Delta is delta of y naught is go forward, so y1 minus take the difference y naught. And what is it? The same value is nothing but in terms of nabla, it is nabla of y1, not nabla of y0. So doing is same, but representing the values are different. So for forward, it is nabla of delta of y0. For backward, it is nabla of y1. Because for nabla, we are starting with the value and taking the difference with previous value. And what is forward? We are going forward and taking the difference with the given value itself. So this is how the connection is there. Again, don't worry much about the connection. Just understand how you are constructing the table. And one more thing, because it is called diagonal difference table, diagonally, so you should write the values diagonally. So how you get diagonal value? Then this value you should write in between y0 and y1. Don't write in the same line. You should write these values in between those two values. Similarly, delta y1. Delta y1 you should write in between y1 and y2. It is same as nabla y2. That also you should write in between these two. How you calculate? It is delta y1 means you go forward of y1, it is y2 minus value y1 itself. And why it is nabla y2? Nabla y2 is starting with y2 and taking the difference with previous value. So therefore doing calculating the value is with the same difference, but its value differs. Here delta y1, here it is nabla y2. I hope you following. Next is in between these two comes delta of y2 as well as nabla y3. So delta y2 is y3 minus y2. So now delta y2 is go forward y3 minus y2. The same as nabla y3. Why? Because nabla y3 indicates to start with the value, take the subtraction or difference with previous value. So this is how. So similarly, this as well as this. So you have to go further because you have the pairing to construct further. So go to next. Next is delta square or nabla square. So how you get delta square? It is delta y1 minus delta y0. Delta square y0 is delta y1 minus delta y0. Why? Because you are constructing delta of delta y0. So therefore delta y0 is y1 minus y0. You are operating delta on both sides. So delta of y0 is delta square y0. So it is y1 minus y0 becomes delta y1 minus delta y0. So you don't again worry much on that. Just you take this value minus this value. That's all. Here also you are taking nabla y2 minus nabla y1. This minus this. For forward, this minus this. For backward, this minus this. And position is same. But representation is different. Delta y1 in terms of nabla is nabla y2 minus nabla y1. Similarly, you do this minus this is same as doing this minus this. What you get? You get delta square of y1. It is delta y2 minus delta y1. Or what is nabla square y3? Nabla y3 minus nabla y2. But value is same. So similarly, you complete this rest of the things. Okay. Similarly, delta cube or nabla cube. You construct in the similar manner. So again, you can go further because you have pairing, isn't it? So delta to the power 4, nabla to the power 4. This minus this, you write in between here. This minus this, you write in between here. Again, two pairing is there. So you can take the difference. So go for last one, delta to the power 5 or nabla to the power 5. So it is this minus this. So this is what I defined. So this is how you are constructing the diagonal difference table. Why it is stopped in the fifth order? Because next pairing is not there. So it is either delta to the power 5 y naught and doing is same this minus this or lambda to the power 5 y5. So this minus this. Values are same. So next this is either this or that. Only one value. So next you are not having any two values to take the difference. Therefore, the table stops there. And next, one more thing is, if you use forward difference, in the next interpolation formula you are going to consider, you are always considering only the first value. So, this is the path. So, these are the only values we are preparing in the interpolation formula. Okay. And if you use backward difference, then these are the values you are preparing in the interpolation formula. These are the grouping of the values or path of the values you are substituting in the Newton's backward interpolation formula you are going to consider later. And these are the only values you are substituting in the Newton's forward interpolation formula you are going to take in the later stage. So this path you just remember. But anyhow, you may ask why rest of the values if you are writing for if you are considering only this, because without completing this you can't go further. So therefore construction should be complete, then later you are considering only in NFIF, Newton's forward interpolation formula, only these sets, and for Newton's backward only these sets. So next I move on to, so what I did, I have defined now finite differences, particularly only for equal intervals. For unequals, I'll take at the stage of next interpolation formula. So finite differences are over. Next, I move on to this part, interpolation and extrapolation using Newton's forward and backward difference formula. Okay. These are later stage. Wherever I am showing in the animation there. Okay, so we move on to the next. So next I prefer what is interpolation and extrapolation using Newton's forward and backward difference formula. So what is interpolation or extrapolation? They'll give a set of values of n plus 1 set of values of y for the unknown function y equal to f of x corresponding to n plus 1 equidistant values of x. Equidistant values means difference between consecutive values of x should be same as h, and that h we are calling as step size or step length. Okay. Then what is the meaning of interpolation? Interpolation means you should get the value of y for the intermediate values of x. So you are knowing what is y naught for x naught, what is y1 for x1 for the function y equal to f of x. Suppose I need the value of y for the values which is x naught plus x1 by 2, which is in the middle of these two. Then what is the value of y? The method of finding that is called as interpolation. Okay, or I want the values between xn plus 1 and xn, that is average of xn plus 1 xn, or in between any value xn plus 1, sorry, xn minus 1 and xn. I want the value of y for that, because we have only n plus 1 set of observed values of y, not all the values of y for each range from x0 to xn. So I need to find that. So what I do interpolation. Okay, so sometimes I want to get the value of y for the values of x which are to the right of x naught at a shorter distance. Then how to find that? That method of finding we call as extrapolation. Similarly, if I need to find the value of y for the value of x which is to the right of x and at a shorter distance, then also it comes under extrapolation. Okay. So for equal intervals, we are preferring two formula. So this is same as this is here. Interpolation for extrapolation, those values of x need not be at equidistance. Suppose those values of x are at equidistance, then what are the formula of finding doing interpolation and extrapolation that we take now? Okay, so one is Newton's forward interpolation or extrapolation formula for equal intervals. So this is the condition. Okay, then formula you have to by heart. Either you want it, you take down. So y r. R is any value in the intermediate value of x. So y r. Y at x r. Where x r is the intermediate value of x in the set of values x naught to xn. So how we get that? It is by this formula. It is y naught plus r into delta y naught plus r into r minus 1 by 2 factorial into delta square y naught, etc. It goes. Okay. So where r is any real number, and for forward difference, r is given by, because you want to substitute r, x naught, y naught they'll give, isn't it? So delta y naught, delta square y naught, delta cube y naught, all those values you can substitute from constructing the forward difference table. And one more unknown you need in the formula is r. So how to find r? It is x minus x naught by h. What is x? Where you need that value. And x naught is initial value of x, first value in the x column. And what is h? H is the common difference between two consecutive values of x. It is step size or step length. So this is so. Then what is backward interpolation formula? Two formula are there given by same scientist Newton. So it is given by yr equal to. This is written in terms of initial values of y naught. Everything is in terms of y naught. And here it is in terms of last value of y. So y, you want to interpolate any value of x which is at the end of the table, then you use Newton's backward interpolation formula, and it is given in terms of last values. So yn r into, here instead of delta we are using nabla, that is backward differences. So instead of y naught, one formula if you by heart, then another you can write easily. So instead of y naught, yn. R into, instead of delta y naught, nabla yn. R into, instead of r minus 1, here all comes plus. R into r plus 1 by 2 factorial into delta nabla square yn. plus r into r plus 1 into r plus 2 by 3 factorial into nav log q by n, etc. It goes. And here what is r? R is again different. Here it is in terms of initial value and here it is in terms of last value. X minus instead of x naught, it is xn by h. Hope you are understanding. So next one. Note. Then since you are having two formula, so you should know when you have to use those formula. Okay. So whenever you want to interpolate the value of x, which is in the beginning of the table, then we prefer NFIF. And if it is at the end of the table, near to xn, then we prefer NBIF. So in one sentence, I preferred it. So if it is beginning of the table, if you want to interpolate the value of y that is near to x naught, then we prefer NFIF. And it is at the end of the table that is near to xn, then you prefer NBIF. In the examination, they may ask, using appropriate interpolation formula, you should do the interpolation. Then you should know this point. And similarly, when you have to extrapolate, first of all, the value of x should be at equidistance to use NFIF and NBIF. And second thing, while doing the extrapolation, the desired value of x, which should be at the left of x naught at a shorter distance to prefer NFIF, and to the right of xn at a shorter distance to prefer NBIF. So now we take problems on that. So first problem. So I take the problem from your reference textbook, that is Grewal. So that here in this problem I took both the case using NFIF as well as NBIF. The table gives the distance in nautical miles of the visible horizon for the given heights in feet above the Earth's surface. Okay, so they had given x as height and a corresponding value of y, which is giving the distance from the distance in nautical miles of the visible horizon. Okay, so when you are at the height of 100 feet from the Earth's surface, you may see the nautical miles visible horizon at the nautical miles of 10.63. If you are in the height of 150 from the Earth's surface, the visible horizon at the distance of 13.03 nautical miles. So this is how they had given some observation and they had given in the table as a observed data. Now, what they need is we have to find the value of y when x is 218 feet. Where is it? X 218 feet. It is very close to 200, isn't it? Next, also you need what is the distance of the visible horizon when you are at the height of 410 feet from the Earth's surface using appropriate interpolation formula. So we do that now. Solution. So this is the table they had given. Now I focus on finding what is the value of y when x equal to 18 feet using an appropriate interpolation formula. So we need to interpolate the value of y. Why it is interpolation? Because the value is inside the table, not outside. Desired value of x equal to 218, which is in the beginning of the table. You may ask, it is not in the beginning of the table. Why? Because beginning means it should be either close to 100 or close to 150, in between these two values. But it is close to 200 or in between 200 and 250. What we do is, because interpolation is nothing but the method wherein you are getting approximate value. So here what we do is we neglect, since we need the value of y at x equal to 218 and 218 is close to 200, we better take 200 itself as initial value and we neglect this. Okay, so near to x equal to 200, let us neglect first two set of values in the table, namely 110.63, 150 and 13.03. You can neglect because approximations, so therefore you may. Then because your syllabus is constrained to only NFIF and NBIF, which is preferred only when you need to interpolate at the beginning of the table as well as end of the table, and it is very in middle of the table. Actually, for the values of x which are at the middle of the table, you have two more formula called Bessel's and Stirling's, but it is out of your scope of the syllabus. Therefore, we prefer to modify this table. Okay. So let us take x naught as 200 and consider the table as, so I modified the table now. So what I did, I neglected these two, rest of the values only I preferred here. Okay. Then I give the notation now. So 200 itself I take as initial value as x naught, and this is corresponding value of I as y naught, and this is x1, this is y1, this is x2, this is y2, this is x3, this is y3, and this is x4, and this is y4. I just mentioned the notations there. Now by taking x naught as 200, and we have to find the value of y for the desired value of x equal to, first is 218 feet, which is in the beginning of the table, isn't it? So because it is very close to x naught, therefore we prefer NFIF as I mentioned. So first I write the Newton's forward interpolation formula. This is the formula. Then I have to now interpolate the value of y for x equal to 218 feet. So first I find what is r. R is what? X minus x naught by h. So this becomes what now? R equal to, where you need y value at x equal to 18. So wherever you need the value of y, that becomes x general value. So x you take as 218 minus x naught, the beginning value. Even though 200 is not beginning value, you made it as a initial value. So therefore, replace it by 200 from the modified table. Then h. What is h? Common difference between two consecutive values there. You check there, you get it as 50. Between every two values, consecutive values, difference you get as same there. Therefore, we are preferring NFIF here. So 50. So simplify, you get 0.36. Now you have to find what? In the formula, so you got R now. Now you have to find y naught, delta square y naught, etc. So I prefer forward finite difference table. So I make the table now. So first column for x values, second column for y values, and third column for delta. So what is delta? It is delta of y naught. What is delta of y naught? This minus this, isn't it? So don't bother about nabla y1. First only focus on delta y naught. 16 minus 0.1 minus 15.04 is delta y naught. Then 18.42 minus 16.01 is delta y1. 19 minus 18.23 is delta y2. 21.27 minus 19 is delta y3. Next you go to delta square column. I forgot to write that. So what is it? This minus this gives delta square y naught. Only all for delta square all for y naught here, because you are using forward difference formula. Then this minus this gives so, this minus this gives so. See there, I have written all the values in between those values. Okay. Next you go to third order difference. So delta q y naught is this minus this. Delta q y1 is this minus this. Again two set of values, it goes up to delta to the power 4. This minus this is so. Next you don't have any pairing to take the difference. So here the table stops. Now you prefer which set? Because you are using NFIS, this is the set of values you are preferring here. So substitute now. So this is the formula. So y naught from the table, it is 15.04. R is 0.36 you have found out using x minus x naught by h formula. Delta y naught is first value in the delta column, plus substitute like that. This is delta square y naught is first value in the delta square column. All the first values because of the path. Now you add up using calci, you get 15.70 nautical miles. So what it indicates? It indicates the distance. If you are at the height of 18 feet from the Earth's surface, the distance of the visible horizon is 15.7 nautical miles. So this is how, if with the help of few observed data, you can get the rest of the values with the help of the Newton's forward interpolation formula only when values of x are at equidistance. Okay. Now we move on to one more problem they asked, and the same problem. What is the distance of horizon if you are at the height of 410 feet from the Earth's surface? Now check that. What is 410? 410, is it at the end of the table? Yes. So we prefer now at the shorter distance of last value. So we prefer not Newton's backward interpolation formula. So what it is? Again, I wrote the backward interpolation formula. First, I get R here because I am preferring NBIF. The R value you are getting with the x minus xn by h. So it is nothing but what? X is where you wanted 410 minus h is 50. So 410 minus xn. Xn is the last value in the table divided by h is 50. So you get 0.8. Now you have to find all the backward differences. So here no need to do again the table. Just copy or you see the table. In the examination you are having in the previous page the forward difference table. The same you can use it. Okay. So already I did. So this I copied from the table. This is same table I have done for finding the value of y at x equal to 210. So same table, but here you prefer last set of values because you are using Newton's backward interpolation formula. So substitute that. So what is it? There is a yn becomes here y4. Last value yn is y4 plus r into nab. You modify this. Nabla into yn is y4. R into r plus 1 by 2 factorial. Nabla square y4. Nabla cube y4 up to nabla to the power 4 y4 you should write. Constrain it. Here it is plus etc. You write up to where it exists. Now substitute. So what you get? You get r equal to this and substituting you get these values and simplify you get this. So at the height of 410 feet if you are in the earth's surface, the horizon is at the distance of 21.53 nautical miles. So one more problem I do. Here they had asked to get the interpol. Find the cubic polynomial which takes the following values. So whenever you want to find the cubic polynomial, the thing is you can either use NBIF or NFIF. First you should check whether those values of x are at equidistance or not. They are at equidistance, right? 1 minus 0, 1, 2 minus 1, 1, 3 minus 2, 1. So if they are at equidistance, what you do, either you should use NFIF or NBIF. NFIS is preferred when you want to get the value of x at the beginning of the table or to the right of x naught at a shorter distance. This is at the end of the table or to the right of x and at a shorter distance. But here they haven't asked y for a particular value of x. Instead they asked the polynomial, cubic polynomial for this data. So in such case either you can use NFIF or NBIF. Only thing is you construct the table but don't use both, either NFIF or NBIF, any one. Okay. So only difference is x minus x naught by h. Since you want it in general formula, keep x as it is. Don't substitute. Otherwise, you are substituting x value as where you want y, isn't it? So in the first case, you replaced x by 210. In the second case, you replaced x by 410 or 408, I forgot. So here you keep as it is, x as it is, whenever they ask to find the polynomial. So x minus x naught here is first value 0, common difference is h, so you get x. Now substitute wherever, and this is the set of value because I preferred NFIF here, then substitute, it is y naught is 1, in the y column first value plus r as x, then delta y naught is first value in delta column 1, plus x into x minus 1 by 2 into delta square y naught is minus 2, etc. It goes and simplify, you get the polynomial, cubic polynomial as this. Okay, so this is how you are getting the required polynomial. And also they ask what is later, after getting the polynomial, what is functional value, f at 4. That is what is y when x is equal to 4. No need to do again. You are having the general polynomial, substitute x as 4 here and you get it as 41. So this is the other way of doing. Next, I move on to, so I did finite differences for equal intervals and also interpolation and extrapolation using Newton's forward and backward difference formula. Now I move on to the next topic. It is how to interpolate or extrapolate for unequal intervals. using two methods, Newton's divided difference as well as Lagrange's formula. Okay. So here, first we should know one more differences you should understand first for unequal intervals. So here you have n plus 1 set of values of y for the unknown function y equal to f of x for n plus 1 values of x. No need to be there at equidistance. There equidistance is a must, but not here. Okay. Then what you have to do? You have to either interpolate or extrapolate using the differences. So Newton's general for that you are having two formula, Newton's general interpolation formula or Lagrange's interpolation formula. So first we go for finite differences for unequal intervals. So these are the values of y for n plus 1 set of values of x which are not at equidistance. Then it is, we are defining one more difference, finite difference called delta, small delta, pronounced as delta itself, and is defined as here we are not using operator, we write it in terms of pairing. So any pairing xi and next value xi plus 1 is, we are again the name suggests divided difference. You divide the function y values, difference of y values with difference of x values. That's all. So sum of the first order divided difference. First I take the pairing x0 and x1. So what I do? Functional value of xi plus 1, that is f of x1. What is f of x1? y1 minus f of x0, it is y0, divided by x1 minus x0. This is how we are defining the first order divided difference. Bit difficult than previous one. So this is the notation. In the square, inside the square bracket, we are mentioning the arguments. Arguments are nothing but values of x. Okay. Then similarly, x1, x2 is y2 minus yn by x2 minus x1. Like that you can. Similarly, you can define the second order. Second order have the arguments, three arguments, x0, x1, x2. So whenever you have three values, you read it as second order divided difference. So what you do? You take the first order difference between x1 and x2 minus first order difference between x0 and x1 and divide it by this and this. Skip one middle value. So x2 minus x0. Bit difficult to follow. Similarly, next C set x1, x2 and one more. Leave the first one x1, x2, x3. It is the first order difference between x2 and x3 minus difference indicates you have to subtract first order difference between x1 and x2 divided by x3 minus x1 by skipping the middle value. So this is how we are defining the second order. Similarly, you can define the third order has four arguments, that is second order difference among these three minus second order difference among these three arguments divided by, now I am skipping two values in between x3 minus x0. Like that I can define the third order. Now similarly you can define fourth order, fifth order, etc. nth order. Now these also can be written in terms of diagonal difference table. First column for x, second column for y, and third column for first order divided difference, next second order, third order. So what it is? It is y1 minus y0 minus x1 minus x0. Gives the first order difference between the arguments x0 and x1. Similarly, among these two first order divided differences y2 minus y1 minus by divided by x2 minus x1. Similarly this. Now go to second order. So x0, x1, x2. x0, x1, repetition x1 is not required, right? x2. What you do? This minus this or this minus this by this, skip one value. So this is so. And similarly second order. And third order having x0, x1, x2, x1, x2 repeated, don't write x3. So four arguments means third order divided difference. So this minus this divided by, now you skip two values in between x3 minus x0. Like that it goes. Again in divided difference we prefer first set only. So this is the path you remember. Now I use first formula, that is Newton's general interpolation formula. So it is given by yr, y, that is y value at the intermediate value of x is y0, first value, plus first order difference, sorry, x minus x0 into first order difference among first value x0 and x1 plus this one repeated x minus x0, add one more difference x minus x1, and first value in the second order table, plus this one into this one, plus one more term x minus x2, and into second order. Like that it goes. Now we do problem. So given the values this, you have to find f at 9. So where is f at 9? F at 9 is in between 7 and 11, isn't it? And first of all, you see the values are in the examination. Either they mention, generally they mention which formula. If they don't, first you see check whether the values of x are at equidistance or not. If they are at equidistance, either you use NFIF or NBIF. NFIF if it is in the beginning of the table or to the left of x naught, and NBIF to the end of the table or to the right of xn. And if they are not at equidistance, then don't prefer NFIF or NBIF. You have to prefer either NDIF, that is NGIF, Newton's divided difference or Newton's general interval, same they are, and that you have to prefer, or one more last formula Lagrange's. Okay, here I prefer they mentioned to use Newton's divided difference formula. It is nothing but Newton's general interpolation formula, because here the values of x, see there 7 minus 5 is 2, 11 minus 7 is 4. So difference is not same. So therefore we have to use that I mentioned here. So we go to next. So first what we do, we prefer the divided difference table. First column for this x not value. Better here you give the notation. Okay. So 5, 7, 11, 13. Next y value. So here you write. Even though you don't mention the notation here, it's okay. But in Lagrange's, you always better go for notation. Otherwise, you get a confusion with taking the values of x and y, and a small difference leads to wrong answers. And you won't get marks, because in maths we are giving value marks for steps. Therefore, now you do the first order difference. What you do? This minus this by this minus this. Next is this minus this by this minus this. Next is this minus this by this minus this. Like that you complete the first order. Second order is this minus this by skip one value. 11 minus 5. That is what I wrote here. Next this minus this by this minus skip one value. 13 minus 7. See, I skipped the 11. Next, last one is this minus this by 17 minus 11. I skipped this. Now, third order. Third order it was this minus this. By now you skip two values. So, 13 minus 5. And then similarly, this minus this by skipping these two, 17 minus 7. And because you have two more, here you got 1 same. So, anyhow, this 1 minus 1, 0, 0 by anything 0. Therefore, this table you can stop here, or even though you write the next table with the different 1 minus 1 by shifting 3, skipping these three values, 17 minus 5, you get 0 by something 0. It won't contribute anything. Therefore, enough. No need to write that column. So stop there. Then always you prefer the first path. Path is this. All the first values. Now you write the formula and substitute the corresponding value. You get f at 9 as 8, 10. Then sometimes, generally in this category, they ask a polynomial. So this is why we prefer NGIF or NDIF here, because difference between these two consecutive values are you are not getting same. So therefore, and since they asked a polynomial, you first complete the table as I did. Here I didn't write any notation, directly I can do. So this minus this by this minus this gives the first order as minus 404. 5 minus 33 by 0 minus of minus 1. Here you should be careful, minus of minus. If you are not doing with the consciousness, you will do mistakes. So be alert while doing the calculation, particularly in a calci. So you get minus 28, because plus minus everything counts that. Then 9 minus 5 by 2 minus 0, 2. This minus this by that, 5 here, 5 I missed it. 5 minus 2 is 4, 4. Then this minus this divided by, now you skip the value, 0 minus of minus 4, 94. Like that you complete the table. Then substitute, take the path of first values, substitute in the table, simplify, you get. And one more, since they asked a polynomial, In the place of x, you keep x as it is and go on simplify, and you get at the end the polynomial value as this. 3x to the power 4 minus 5x cube plus 6x square minus 14x plus 5. Then we move on to the last formula of interpolation and extrapolation is Lagrange's. So what it is? It is, here also values of I need not be at equidistance. So LFI, here the advantage of Lagrange's interpolation formula is you are not preparing any table there. Directly this formula and you are substituting. So what is the formula here? So f at x or y at intermediate value of x. It is, see the symmetry here. The first term is x minus, first value you skip. X minus, you start with x1. X minus x1 into x minus x2 into x minus x3 up to last value. X minus xn and divide it with here the same term and only changes at the place of x you replace by x naught. Suppose you wrote here x minus x naught and here what happens? X naught minus x naught becomes 0 and 1 by 0 is infinity, infinity into anything infinity. So it is not defined. Therefore, we are skipping x minus x naught term here. So be careful. So here I skipped x minus x naught and wrote x minus every difference with every values of x up to xn. And then the same term with replacing wherever x by x naught value and multiply it with y naught. Plus next add in the second term, you write x minus x naught. Now you skip x minus x1 term. Then take the difference of x with the rest all x values and divided by same term with wherever x you replace it by x1, what the term you skipped into y1. Like that till the last term you have to add. Okay. Then this is the problem. So they are not at equidistance. Either you use NGIF or LIF. Here I preferred what Lagrange's interpolation formula because they are not at equidistance. Now this is the formula. The beauty of Lagrange's is we are not doing any table there, but here mentioning the notation is very, very important. Otherwise, every time if you go for substituting, you may make mistake. So if it is clearly written the notation along with the values, then by mere mechanical checking you can substitute the particular value properly. So that is the advantage. So now according to what is y1 last value x4, so I constrain the formula to particular value. Here I don't write etc. The general formula it is up to etc. Here it is particular value. And substitute the particular values, simplify, you get the value. Problem 2. Here also they may ask to find the polynomial. So what is the only difference? First of all, it is not at equidistance. So we prefer either NGIF or LIF. Then in the formula, write the notation for those values starting with x naught, corresponding value as y naught, up to x3. Then only the difference is in the formula. Constrain it to x3 now. Then keep x as it is. So here in the formula, so I carried that table. You keep the x value as it is because they asked the polynomial as you did in earlier stages. So simplify that polynomial and you get the polynomial as this. This such type they generally ask polynomial in unequal intervals. This. And later they asked what is f at 3. So in the polynomial itself replace x by 3. This is how I completed what is in interpolation. Lastly, one more part, it is inverse interpolation. So inverse interpolation is only for Lagrange's because for other formula, because we are preferring table, changing x and y is not feasible. So therefore, in the Lagrange's only, we are preferring inverse interpolation. What is in inverse interpolation? You need to find the value of x for the intermediate values of y, reverse process. There you found the values of y for the intermediate values of x. Here it is finding the value of x for the intermediate values of y from the observed data. So why we prefer Lagrange's only? Because here x and y arbitrary representation. So just mere interchanging of x and y in the Lagrange's interpolation formula, you can do the inverse interpolation. See there. What is inverse interpolation? You are finding functional value of y at r. That is x value at certain value of y. So what we did, there you had x minus x1. Here it became y minus y1. X minus x2 change to y minus y2. Only mere interchange wherever x by y, wherever y by x, and suffixes you retain as it is. And here there we multiplied by, sorry, here I made mistake, it is not y naught, x naught. So there we multiplied by y naught, here it should be x naught. Only that change. Then we take problem on that. So here this is the problem. They asked what is value of x for y equal to 12. You want to get value of x, not y, for y value. So you want when y is 12, 12 is in between these two, isn't it? What is y? Your answer should be in between. See first nature of the values. They are increasing, isn't it? So therefore you have to get the answer in between 2.8 and 4.1. Not always. First, you should check the nature there by observing the data. Okay. So, since you need the value of x for y, so I have to prefer Lagrange's technique, that is Lagrange's inverse interpolation formula. Here also better you give the notations. Then, okay. Then prefer inverse interpolation formula. Here x naught it is, not y naught. Then I constrained it to, okay, y5, then x naught. So careful while substituting. Y. What is y? You need value of x at y equal to 12. So therefore y is 12 minus y1. What is y1 from the table? 6.8. Like that each value you substitute there. Simplify, you get value of x at when x is y equal to 12 is 3.55. And apply Lagrangian formula to obtain the root of the equation. So what is root? What is root of f of x equal to 0? It is those value of x for which y is 0. So therefore, whenever they ask to find the root, you use Lagrange's inverse interpolation formula. So this is so all the notation for the given values, then take the inverse interpolation, then write the inverse interpolation formula. And thing is, you want value of x for which y is 0. So what you do, replace wherever y by 0 now. That's all. That is the only difference. Whenever they ask to find the root of the equation, you replace wherever y in the Lagrange inverse interpolation formula by 0 and simplify. You get the value of x when y is 0 as this, which is the required desired root of the given function. So here I completed the first part of numerical methods, that is interpolation and extrapolation. Now I move on to the next part, the solution of polynomial and transcendental equations using two methods, Newton-Raphson and regular falsi. Okay. First of all, you should know what is algebraic or polynomial equation and non-algebraic or transcendental equation. So first of all, what is the meaning of solution? The value of unknown which satisfies the equation f of x equal to 0 is called the root of the equation or solution of the equation. So m is the solution of f of x equal to 0. Then if you replace x by m, this equation should satisfy f of m equal to 0. Just now we have found the root of the equation from the given set of observed values using Lagrange's inverse interpolation formula. And here we are not having any observed data, we are having the equation. That is the difference. Then how to find its root using numerical method. Here also we are preferring interpolation formula. That is, we are preferring the formula which should be used repeatedly to approach the required root. So here, first of all, we understand what is algebraic equation. Algebraic equation is a equation which has the algebraic number x in it. And what is transcendental? Any equation having the operators in it, like e to the power x, log x, or trigonometric function. Such equations are transcendental equations. Then first I prefer regular falsi method. So before going to regular falsi method, first you should know where the root lies graphically. So take a graph. So this is the graph of y equal to f of x. What is the meaning of finding the root of algebraic or transcendental equation? Those values of x which are making y as 0. So you are very well know that where y is 0 only along the x-axis. So root should be along x-axis. So the graph should cross x-axis at least once, then only that function or the graph of that function y equal to f of x, if it crosses the x-axis at least once, then it has a roots. Suppose it crosses twice, then it has two roots. If the graph crosses three times, then it has three roots, like that. At least once it should cross. Suppose you have graph like this, then that graph for which function, that function is not having root at all. Okay, so it should cross. So now, since it crosses, now where first you should assume in the beginning where the root lies, in between what values. You have to assume that. So for that, how to check? For that, you start with the giving values of x as 0. Then get the functional value. Suppose the functional values of first value and next value differ by sign. Suppose the root is, the equation is only this, then I take x, a value here, b value here, and root is not there because root is always lies on that. So functional value of a should be greater than 0, f of b should be less than 0. Then only in between those values the root x lies. In between a and b, the root x lies. Suppose it is b and f of b here. Suppose it is here. Then in between a and b, root won't lie because root is always on x-axis. Therefore, we take f of a either, if f of a greater than 0, f of b should be less than 0. Then only root lies between a and b. Or if you get f of a less than, suppose you take this as f of a, or the graph is like this if you take, sorry. If you take the graph like this, then b is, f at b is less than 0, f of a greater than 0. Then only it crosses x-axis once and root lies between a and b. So only necessary condition is functional value at those a and b should differ by sign. Then only root lies in between those two values a and b. So with this knowledge, we get now root of this algebraic equation because it is not transcendental, it has only x variable there, using regular false, and they ask either to repeat the formula how many times or correct to some decimals. So according to that, you should decide up to how many iteration you have to do. Okay, so this is the given equation. F of x equal to, first what you do, you have to get those values of a and b, wherein in between those a and b, the graph should cross x-axis because roots of equation lies always on x-axis. Along x-axis, y is always 0, not anywhere. So therefore, what I do, I start with a given equation, and it is in the form of f of x equal to 0. So therefore, what is f of x? F of x is this. So I write what is f of x. Next, first I put x equal to 0. That is, I get what is f at 0 now. Substitute here. 0 cube minus 2 into 0 minus 5. You get minus 5. Then I put next x equal to 1. Generally, this works. F at 1. Now you substitute here x as 1, you get minus 6. Both are negative, right? So therefore, you root won't lie between 0 and 1. So next you put x equal to 2. So what is f at 2? Substitute here x as 2. You get minus 1. Check now. Is this is negative, less than 0. This also less than 0. So you can't say root lies between 1 and 2. So go further. Put x equal to 3. F at 3. You get 16. See here, f at 2, it is less than 0. F at 3, it is greater than 0. Now you can stop and say the root lies between 2 and 3. So when functional value differ by sign, then root will lie in between those two x values. I hope you understood. So therefore, since clearly f at 2 is less than 0, f at 3 is greater than 0, you can say now root lies between not these two, root is x value. So root lies between 2 and 3. Now, you can, because regular falsi method is the having slower convergence than Newton-Raphson method. So you can make the difference between these two much lesser. How? You start with, again, once you understand in between 2 and 3 root lies, you can take any in between value. Say I took the average of this 2.5 and substituted, I got greater than 0. So f at 2 is less than 0 and f at 2.5 is greater than 0. You may take directly 2 and 3 also, because they asked to 3 decimal places. If you make the difference between the x values you are taking, then your convergence will be faster. Therefore, I made it further. I took 2.5. So this is less than 0 and discard this, take this. It is greater than 0. I can say root lies between 2 and not 3, 2 and 2.5. Or you can check for f at 2, then start with f at 2.1, then there also you get negative, so root don't lie between 2 and 2.1. Next to get f at 2.2, there also you get negative, so you can't say root lies between 2.1 and 2.2. But at 2.5, you can do one more checking like this, and at f at 2.5 you get greater than 0, then you stop, because already you have where it is less than 0. So you can conclude now root lies between 2 and 2.5. After that, you go for first iteration. So you take now first value a as 2 and b as 2.5. And we have seen in the previous slide, f at a is point minus 1 and f at b you got as 5.625, because of f of x is x cube minus something. Now regular falsi method has this formula. This is the iteration formula. This you have to by heart. X equal to a into f at b minus b into f at a by f of b minus f of a. Easy to remember. Now substitute. So what is first value? First iterational value. It is, you are not exactly getting the root. You are going closer to closer by repeating the formula. That is the beauty of numerical methods. So what is x1? A. What is A? You took 2 into f at b. F at b is 5.625 minus b. B is 2.5 into f at a. F at a is minus 1. Divided by f at b. 5.625 minus of minus 1. Use cal c to simplify. You get this. Next, what you do? You get f at x1. F at x1 is f at this value. And you get negative. Once you get negative, check in the previous slide whether which is lesser than and which is greater than. So f at 2.0755 is less than 0 and f at 2.5 you have seen earlier it is greater than 0. So root lies between these two values. So go to second iteration. Now substitute, you get this value. Then get what is f at x2. Then you get negative, so less than 0, and where it is positive at f at 2.5 greater than 0. So go back, and wherever once it is lesser than 0, from previous line itself you are going to check where it is greater than 0, and that value of x you have to prefer. Don't start with the beginning, go backwards to seek where f at x is greater than 0. You get f at 2.50. So root lies between them. So take A and B so and simplify. I'll take next problem because there I have clearly mentioned the procedure. So I skip this method. So go on check. So see here. Here I explain. So A is 2. F at A you got minus 1. B has 2.5. F at B has this. So X. Use this. Substitute those values respectively here. You get this. Get F at 2.0755. You get this. Now what is A and B role? Here, this is negative, right? So where it is negative, at this. So therefore, take A as not 2. The modified value of 2 is now this. So I took A as now. At the place of A, I took 2.0755 and I changed f of x as now f at a is. And where it is positive at 2.5. This is negative, so I need here positive value. So discard this now. Because of better than a, now a is this. So 2.5 this. Now use the same formula, you get this. Take functional value. Here also you get a minus, isn't it? Now, what you do in the same formula, first you replace a by 2, b by 3, 2.5 and functional value simplified. In the second stage, you replaced a by instead of 2, you replaced it by 2.0755, better value, and b as it is. In the next, since it is negative, now discard this because it is also negative. Better than that, you got this now. So now you in the formula, you take a as 2.0908. Corresponding value you carry here and f of x becomes now f at a. And this you take as it is. Now you substitute here, you get this. And next, get functional value f of x. F of x is some x cube minus something they had given. There in the place of x, you substitute this value, simplify, you get this. Right? Then this is also negative. So what you do? This better than this, you have this value now. So replace this value by this itself, 2.0938, and corresponding value is this. Then this you retake. One should be one here it is negative, so you should take another as positive. Now you substitute here, you get this. Now functional value you get this. Next, here this is negative and at b it is positive. So instead of this, you got better value now. So take this now. Instead of this, you take replace it by this negative. This as it is, substitute you get this, you get. See here, they asked the value, decimal value should be correct up to 4 decimal places. 3 decimal places. It is same up to 3 decimal. So therefore you stop now and say that the root of the equation correct to 3 decimal place as x is equal to 2.095. Next, find the real root of the equation by the method of first position correct to 4 decimal place. See here. This is x log x to the base 10 equal to 1.2 implies, so f of, compare this. So take everything to one side equal to 0. So f of x is this. So don't take f of x only this. First you should compare this with f of x equal to 0. So you have to take everything to one side. So f of x is this now. If you skip this, every value goes wrong. So try to understand the concept properly. You have to take f of x equal to 0. So now as we did earlier, f at 1, put x as 1. So 1 into log 1 to the base 10 minus 1.2. So it is log to the base 10. So you have to press in calci log key, not ln key. Okay. If it is to the base 10, log key. If it is not mentioned, base is not mentioned, you have to press ln key in the calci. Here it is to the base 10, so press log key, log 1 to the base 10 it is, and you get negative. Put x equal to 2, you get negative. So f at 1 is negative, f at 2 is also negative, so discard. Root won't lie between 1 and 2 now. Go to x equal to 3, you get positive. So f at 3 it is positive, f at 2 is negative. So they are differing by sign. So you can say now root lies between 2 and 3. So root lies between 2 and 3. Now in between value take f at 2.5, you get negative. So you can say now clearly f at 2.5 less than 0. So another one you have to prefer greater than 0. Where it is at f at 3 greater than 0, root lies between 2.5 and 2.5 and 3. Because this method has slower convergence, you make the difference between x much lesser than previous. Now first iteration. So I did it. A equal to I took 2.5, F at A I calculated in the previous slide this, B as 3, F at B as 3. Then I used first iteration this, and by taking A as that, B as that, F at A is this, substitute, You get the value as 2.73492. Then next you get f at x, f at x1. This is now x1. So f at x1, you get you substitute in f of x, so that is x into log x to the base 10 minus 12. X, wherever x you replace it by this value. Simplify using calci, you get negative. So I wrote here. So if this is negative, and where it is positive at 3. So therefore I neglected this. Better than 2.5, I can replace by this new value now. So and its functional value. So f x becomes a, f of x becomes f at a. B I retain because one should be negative, another should be positive. Next, I simplify. I go to the second iteration. In the second iteration, I take A as this, B as this, and in the formula I substitute, and I get again here x3 as this. It is negative, therefore root lies between. So I replace now this by this, and this x3 becomes now a, and this is this 3 I retain, and I do. So go on, do that fourth iteration till you get the somewhat same answer. See here, 2.7406, 2.7406, up to 4 decimal it is same. I think they have asked up to correct 4 decimal place, so you got the answer. So next, this I skip. They had given the initial value 0 0.4 and 0 0.6, and you have to find the root for this. It is a transcendental equation because it has operator e to the power x as well as trigonometric function cos x. So what we do? So one thing you should be careful, whenever you are finding this, your calci should be cos of x. Here what is x? X is a real number, not in degrees. So your calci mode should be in a radian. That is very, very important. Keep the mode of calci in radian mode, then only you should do. Because here x you are giving 0, 1, 2, 3, etc. So they are not degrees, they are radians. So therefore, keep the mode of the calci in radians, then you do the problem. So x you take because here they had given 0 0.4 and 0 0.6, no need to check from x equal to 0, x equal to 1. They mentioned, and they are not in degrees, they are in radians. Keep the mode of the calci in radian mode, then you do, you get negative. F at 4, F at 0.6, you get positive. So this is differing by sign, functional value. Therefore, root lies between 0.4 and 0.6. So go to first iteration. So take A as 0.4, B as 0.6, substitute in the formula, you get positive. Now, this you get negative. So therefore, you go to take one is positive, one is negative, and continue. You get go on doing it until you get 4 decimal place accuracy, depending on that. Here I explain. So first I take A as 0.4. I found f at A using the formula x e to the power x minus cos x. Wherever x I replaced by 0.4 and simplified using calci, I get negative. B I put 0.6. F at B means I should get f at 0.6 as 0.6 e to the power 0.6 minus cos of 0.6. I get positive. Then I replaced A by this, f at B by this minus B by this, f at a by this by f of b minus of minus plus b. It becomes simplify, you get this. Then get functional value at this. So you get this. Now this is negative. So you have to seek among that where f at value is positive. Here it is positive. So therefore discard 0.4 by 0.5095. Carry this here and keep this as it is. And again substitute a by now this f of b by this minus b by this, f of a by this divided by this minus of minus plus this, and simplify, you get this, and get f at this. F of x is x e to the power x minus cos x. Substitute x as this in that formula, you get negative. Again it is negative. Seek for where in among this it is positive, that you retain, but replace negative value by Instead of this, I take now 0.51721, this as it is, and this you get negative. Again replace this by now new value, this you retain, get that. So you get same value up to 4 decimal, stop it. Sometimes they may ask up to 3 decimal, then you may stop in here in this stage itself, because 0.517 here also 0.17, you can stop in the third iteration. If it is 4 decimal, this is not same as here up to 4 decimal, so I need to go for next iteration and then I stop. So depending on how they ask. So this is about the regular falsi method. One more solving polynomial or transcendental equation by Newton-Raphson method. So Newton-Raphson method, in that it is a formula is iteration formula. In the regular false iteration formula is x equal to a into f of b minus b into f of a by f of b minus f of a. But in Newton-Raphson method, there you need to start two initial values. Here you need only one initial value. The general iteration formula is this: xn plus 1 equal to xn minus f at xn by f dash at xn. So this is the iterative formula for Newton-Raphson method. For getting the root of algebraic or transcendental equation, f of x equal to 0, where f dash is derivative of f. So I take problem on that. Find the positive root of this, correct to 3 decimal places. So this is f of x. Get f. Now you first get where the root lies. So put x, start with x equal to 0. F at 0 is 0 to the power 4 minus 0 minus 10, you get minus 10 negative. Put x equal to 1, substitute there, you get minus 10 negative. So since both are lesser than 0, root won't lie between 0 and 1. So proceed further. Put x equal to 2, f at 2, you get 4. So f at 2 is positive. So if f at don't prefer this, better than this one value. So this is negative, this is positive. Functional values are differing by sign at those values of x. So therefore root lies between x1, 1 and 2. Here no need to further make the difference between them much slower as you did in regular falsi, because Newton-Raphson is having faster convergence. It is enough. So what you do among 1 and 2, you take any one of the values. So either you take x as 1 or 2 or in between any values. Before that, because you need a derivative of f of x to substitute in the iteration formula, next you get what is f dash of x. What is f of x? Oh, x to the power 4 minus x minus 10. So what is f dash of x? You differentiate. What is differentiation of x to the power 4? 4x cubed. Minus differentiation of x is 1. Minus differentiation of 10 is 0. So you got it. Next, go to first iteration. So what is general formula? Xn plus 1 equal to xn minus f at x1 by f dash at xn. So first put n equal to 0, you get first iteration, it is x1. So you are approaching the real root by repeating the formula. So x0 is 1 initial value, then x1 is by next iteration, first approximate value for the desired root. So I put n as 0. So it becomes x1 equal to x0 minus f at x0 by f dash at x0. I took x0 as, you can take any of the values. Either you can take x0 as 1, you can take x0 as 2, or any value in between 1 and 2. I took middle value 1.5. You may take anything you wish. In the problem, by taking x0 as certain thing, then you can't decide yourself. Otherwise, it is of your choice. Now, f of x is here x to the power 4 minus x minus 10, and f dash x is 4x cube minus 1. So first get f at x naught. It is f at x naught is 1.5. Substitute here 1.5 to the power 4 minus 1.5 minus 10. To get this, f dash at x naught is 4 into 0.5 to 1.5 to the power 3 minus 1, you get this. Now substitute in the formula. x1 is 1.5 minus f at x naught is, better you take the bracket here, minus 6.4375 by 12.5, minus of minus becomes plus, use the calci, you get 2.015. Now go to second iteration. Here iteration is easier, no need to replace anything. So x2, put n equal to 1 now. So it becomes x1 minus f at x1 by f dash at x1. x1 you took as a, now the value you got earlier, it is 2.015. So f at x1, substitute here this f dash at x1, then substituting the formula, you get 1 point. Because f of x is this, I substituted x1 as x as x1, it is 2.015. The 4.015 to the power 4 minus this minus 10, you get this. And f dash of x is this, so 4 into x1, 2.015 whole cube minus 1, you get this substitute. So like that, you go on, repeat it, and you get fourth iteration. Sometimes they ask to do the iteration 4 times, like that they mentioned, or correct 2 3 decimal place or 4 decimal they ask. So you do go on, compare always the values of x values, x3, x3 you get 1.8556, x4 also that. So answer will be same up to 3 decimals, so stop now. So this is how you have to do. So I wrote the table there. So I put n equal to 0, xn I took as this, f at xn is this, f dash xn is. I substituted here, I got 2.015. Then put n equal to 1 and take xn as it is x naught, this is now x1. You take this, get this, substitute in the formula, you get this. Then 2, you take now this, instead of this, a better value this, then substitute here, you get this, like this, and this, 3. See here, they are differing, they are not same up to 3 decimal plus. What about in this set iteration? Is it same up to 3 decimal? Yes. Now you stop and conclude that the root is correct of decimal place. So here also is x sin x plus cos x near x equal to 5. Here they mentioned x not equal to what? There we have found it. So here x equal to 5 you take, and very careful your trigonometric terms. So keep the calcium of mode of the calcium in radian mode. Otherwise, you don't get proper answer. So do the same. Get f dash of x. I have done all the differentiation. But if I explain all those, it takes time. I don't want. I use product tool here and differentiation of cos x, the product tool and simplified, and then go on doing it to get that values. Such types of problems are very important. Okay, so do that. And whenever you get the decimal values are differing by whatever the decimal they ask, then you stop. Okay, this also one of the problems. So if I go on explaining this, I won't enough, so I don't want to explain all those. One of the important method here, you should be a bit careful about certain properties. I don't want to do that because time is very short. Okay. Try yourself. If you have any doubt, I will give the contact number. You can clear your doubts. Okay. Sometimes they ask you obtain iterative formula to find 1 by n using Newton-Raphson formula. So here you want to find what is 1 by n. So they haven't given as earlier what is f of x. Here you have to make it what is f of x equal to 0. So what it is, you don't know what is 1 by n. Let that be x. So but if you take x as 1 by n, then if you substitute in the formula, you get back again the same formula. Therefore, in the beginning itself, or check it once by trial and error method. Since you won't get an iterative formula in terms of variable, then don't prefer this. You change it. So I took n reverse. I reversed the formula by cross multiplying n as 1 by x, and I took f of x as 1 by x minus n instead of taking n minus 1 by x. Okay, then f of x is so, differentiating you get f dash x is so. The only change in the previous formula and this formula is that they had given f of x equal to 0 directly. Here you haven't given, you have to make the equation by taking 1 by n. Your interest is to find what is 1 by n. So unknown to you. So therefore, you take let 1 by n as x and proceed. so that you made the equation required as what is f of x. Then as usual, you go to complete it. Okay. You get the required value of 1 by n. Root 5. Find root 5 using Newton-Raphson method. So you can use get directly from the calci what is root 5. But behind the calculator, calculator also should calculate that. What is the algorithm behind the calculation? The same idea. Okay, they have made the program for that. So this is the program behind that. So what you do, first take root 5. Our you wish is to get what is root 5 value. So we are it is unknown to you. So take let root 5 equal to the value x. Then don't keep the equation in terms of fractional power. It should be always integer power. So first you square it. So what you get, x square equal to root 5 whole square. So 5. So x square equal to 5. Or always write it as f of x equal to 0. So x square minus 5 is 0. So f of compare then f of x is x square minus 5. Then as usual differentiate it. Then go on, use the formula and do till you get the required accuracy. So this is the Newton-Raphson method. So here completes the second part in module 5. So solving Newton-Raphson and regular falsi method. The last part is numerical integration. So in numerical integration, we are not using any method of integration. Instead, with the set of values of x and y, with the mere by hearting the formula, we are able to do integration of certain definite integral. It is not very general method. So some definite integral value can be easily calculated with the method of numerical integration. So integration is a definite integral. Integral lower limit is x naught x and y dx. So from a set of observed tabulated values. So if it is applied for a function of single variable, we call that formula as quadrature formula. Okay. So they'll give a set of observed value of the unknown function y equal to f of x, where at equidistance, this is very, very important as we are preferring for NFIF and NBIF application. Then here step length should be same, and we have to take certain conditions here by knowing the certain things. What is it? Xn equal to x naught plus ns. How to find h? You rearrange this. This you know. Xn is in terms of x naught is x naught plus nh because they are at equidistance. Now rearrange this equation for h. What it is? Xn minus x naught by n. So what it is particularly in the given problem? Xn is the upper limit. So mention h you get by using this formula. Upper limit minus x naught. X naught it is lower limit. N is number of equal intervals you can form from the given set of values of x. So how you can? With the n plus 1 equidistant set of arguments. Arguments are nothing but values of x. We can make n number of equal intervals. One less. So 5 set of values if they give 4 equal intervals you can make. This you go to conditions, you better keep it in mind. With this knowing, your syllabus is constrained to three formula. One is Simpson's one-third, next is Simpson's 3/8, and last one is trapezoidal rule. In Simpson's one-third rule, the formula is, see here, the beauty in numerical integration is they are not using any technique of integration. Mere substitution of observed values, you are able to evaluate the integral value, definite integral value. That is the very, very easiest way we are using in our PhD work also, these applications. So it has a very vast application. In my thesis work also, I have applied Simpson's 3/8 rule. So you have to by heart this formula. So because proof is not included in your syllabus, you are the technical people. You are interested only to apply the basics of maths, not how it came. You are not least interested in how it is derived. So It is Simpson's 1/3. Why it is called Simpson's? Simpson's is name of the scientist who invented this formula. So 1/3. So 1/3. H into. See here. In the set of values, y0 and last value has a 1 times coefficient. Then plus add 4 times all the odd suffixes of y plus 2 times all the even suffixes of y. And in Simpson's 3/8 rule, it is 3/8 times h into first and last value has the coefficient 1 and all the multiples of 3 are having coefficient of 2, then rest all values has the coefficient 3. So this is how you can remember the formula. And Wedel's rule is same. See, everywhere you are having integral x naught xn of I dx. See here, and formula are only different. So here in Wedel's rule you have 3/10 times, here 3/8 times, here 1/3 times h into, here coefficient differ according to the formula you have to by heart, and here it is, you better remember the string 1516156, 1516151 or 15 16 15. Then lastly 1, because first and last values always has the coefficient 1. Then 1516151. So 5 times 1, 1 times y 2, 6 times y 3, 1 y 4, 5 y times y 8. Then repeat that. Again start with y6 only, y6 to y12. Then y12 to y18. Like that you have to do. And substitute the string 1, 15, 16, 15, 1. Okay. So this is how you can remember those formula. So according to their asking, you can prefer certain formula. Otherwise, suppose they won't ask using appropriate formula you have to do, then this is the condition. It is asked in one of the gate examination. So if n is multiple of 2, then prefer 1/3. Suppose n is 4 there. 4 is multiple of 2. So then at that case, you have to apply Simpson's 1/3 rule. If n is multiple of 3, then you can use 3/8 rule. Suppose n is 6, you prefer Wedel's rule rather than Simpson. Suppose n is 9, prefer Simpson's rule. If n is 12, prefer Wedel's rule. So these are the condition of applying those rules. Because 9 is multiple of 3 also, 3 only. So prefer Simpson's 3/8. Suppose you take 12. 12 is multiple of 2, 12 is multiple of 3, 12 is multiple of 6. But among that you have to prefer Wedel's, because rather than Simpson's 1/3 rule, he has modified to 3/8 rule. And this method is modified to Wedel's rule. So Wedel is the most fast converging or most accurate, it gives the value. So therefore, if you have n is 12, then prefer Wedel's rather than 2 and 3, even though they are multiples of 2 and 3. Suppose n is 4, then no other go, you have to apply Simpson's 1/3. Suppose n is 9, it is neither multiple of 2 nor multiple of 6, then you prefer Simpson's 3/8 rule. So this is how you can decide. Suppose they won't mention the rule. Usually they mention the rule, using Wedel's or using Simpson's 3/8. Then you can't change the formula. You have to do according to their asking. So here, you have to evaluate integral 0 to pi/2 root of cos theta using Simpson's. I have done this formula using all the three. In the examination, no need to do the problem with all the three methods. Whatever the rule they ask, that rule only you apply. Here I took all the three because I want to save time. Okay. So here also you should be careful. Whenever they give the integration having trigonometric function, you keep the mode of the calc in radians, because here pi/2 is in radians, not in degrees. So therefore keep the mode of the calc in radians and then do. If the mode is in degree, then you won't get appropriate value. So that you should be very careful. Therefore, seriousness on reading is very much required. Okay. So here they themselves said n 6 equal parts. So n is here 6. Okay. So we now get what is step length h using the formula. What is it? B minus a by n, or upper limit minus lower limit by n. What is upper limit? Pi/2. Minus lower limit is 0. What is n? They had given 6. So you get pi/12. So they haven't given the observed value, so you have to make the table. So what is it? F of theta is root cos theta. So I go prefer the table now. Theta. Start with the lower limit 0. Okay, then add the step length. 0 plus pi by 2 is pi by 2. For pi by 12, add h again. Pi by 12 plus pi by 12, 2 times pi by 12 simplifies to pi by 6. Then pi by 12 plus pi by 12 plus pi by 12, or 3 times pi by 12, you get pi by 4, pi by 3. Once you reach pi by 12 next. Once you reach the upper limit, pi by 2, stop the table. Then root of cos theta. What is root of cos 0? Cos 0 is 1, root of 1 is 1. What is root of cos pi by 12? Keep the mode of the calci in radian and check there, you get 0.9828. And what is root of cos pi by 6? This. So like that, from calci you check and give the notation here. This is very important. Otherwise, by in a hurry you will substitute wrong values. So next you better give the notation. First value should be y0, y1, y2, y3, y4, y5, y6. And Simpson's one-third rule is this. So substitute the corresponding value now. It is this equal to, so these are the values, pi by 12, h by 3. Then y0 from the table this. All the values you substitute, you get that. What is Simpson's 3/8 rule? This is the formula. So you get 3 into h is pi by 12 by 8. Then 1, y6 is 0, like that. From the table you substitute, you get that. Did you understand the beauty there? Have you applied any technique of integration? It is generally phobia for students. Integration, when it comes, they'll feel that it is very, very difficult. So here, nowhere we have used the technique of integration. Just we very simply we substituted the corresponding value. And beauty is you got the integrational value. Inverters, write the formula, substitute, you get that. And check the in calci directly you do root of cos integration. In some calcis you can. Then see there among those three formula, Weddell's value will be more accurate. It is very close to the required value in the calcium. So therefore Weddell's rule is most updated method. So here also. Okay. So 0 to 0.6, 7 ordinates. As I said, with the n plus 1 ordinates, we can make 1 less, 6 intervals. So usually n will be even number. That you keep in mind. Okay. So therefore, here you take n equal to 6 as I did earlier. So 0, h is upper limit minus lower limit by n. So 0.6 by 0 divided by n. 7 ordinate means that they mentioned 6 equal in parts. So n is directly 6. Here 7 ordinates. So n should be 1 less. With 7 arguments or ordinates, you can make n with n plus 1 ordinates, you can make n equal intervals. So therefore 6. So h you get 0.1. Start with lower limit, add the step length 0.1, you get 0.1, 0.1 plus 0.1, 0.2, like that. When you reach 0.6, you stop there, and x square is square that, and then you get e to the power minus x square. You get this, or directly you can discard this row. Directly you can get it from calci. Then give the notations for that. Then substitute the respective formula and you get the required. So here completes module 5. I hope you understood.
I don't see any questions on the chat window, ma'am. So
Pardon? You have,
I don't see any questions on the chat window. So
are they asked?
no, they are not asked. So do you have
Shall
anything
we wait
else?
for a while?
Yes, ma'am. You can wait.
But I don't think I can complete 2 more modules in the scheduled time.
Yeah, maybe we can schedule another meeting like this, ma'am.
Okay, then fine.
We'll wait for
So
2 minutes for questions
pardon?
and we'll wait for
Pardon?
2 minutes. If there are no questions, we'll end it, ma'am.
No questions?
No questions, I think. We'll wait for 2 minutes. Right.
How many participants are there?
About 7 to 8.
Only that much.
Yeah, yes, ma'am.
Okay, maybe they are busy with their own works, I guess.
Okay, ma'am. On behalf of IEEE Bangalore section, we thank Vidya ma'am for delivering such a wonderful lecture. And I hope that the students will make use of it for their exam preparation. Thank you so much, ma'am.
Okay, you will inform through mail, right, regarding rest 2 modules?